Okay, so the class recording has just started. Let me share my screen with you. Okay, so you can see this is just yesterday's notes, and we were able to complete the first three parts, 1, 2, and 3, of course. And why does it look like this? Okay, looks like there's some something funny that happened in here. It's there. Okay, that's fine. So what we did was we did a quick review of the laws of thermodynamics, and of course, the zeroth law tells, and before, of course, we looked at some example cases where thermodynamics and statistical mechanics are both important in terms of how to theoretically and experimentally treat and understand the systems. Then thermodynamic viewpoint is the macro states, right? You try to look for variables that will accurately describe the system to allow us to extract the physics that we need. And we also looked at this equation of state. And remember, this equation of state is not normally what you see in your undergraduate classes, right? What you would see in your undergraduate classes is PV equal to nRT, where N is the number of moles, and R is the constant that goes in there, and then the temperature. That's a chemist's definition of the ideal gas law, right? That's not very useful if you want to look at very carefully what's going on. So number of moles is not a fundamental quantity. It's actually how many number of atoms or molecules you have in the system. And so NKBT is the more physically accurate description of what's going on. And this tells you, because KB itself is 10 to the negative 23, your N should be about of the order of 20, like 10 to the positive 23, which is the Avogadro number for these numbers to make sense, right? And only in those cases, the equation of state, PV equal to NKBT, has any meaning, has any usefulness. If the number is much small, like a million, in case of, let's say, Bose-Einstein condensate, then this equation is not useful. Then that's not the appropriate equation of state. You would have to look for another equation of state. And there is actually a field of thermodynamics, a very modern one, called quantum thermodynamics, that looks at quantum systems that are small in number, and very small, not what you would normally treat, consider thermodynamic systems. And so there you would have to come up with a different equation of state. This one is not going to work. Then we looked at the laws of thermodynamics, zeroth law, which basically tells you or prompts you to come up with a definition for temperature, right? Because you consider equilibrium, and the thing that stays constant in two systems that are in equilibrium is the temperature. Energy not, there is always energy exchange going on. What you have is a balance of energy exchange. So if you have two systems, system A is giving energy to system B, and system B is giving energy to system A, but those two processes have found some kind of a balance so that the both directions, there is no one side getting higher energy than the other. But temperature is what stays constant. And then first law is basically conservation of energy. It allows us to define the change in the internal energy of the system through two mechanisms. One is a heat exchange, the other one is the work done. And there are multiple examples of work done. Work done can come as PDV, like in the gases, when you have pressure applied, which causes volume to change, or it could come from mu dn. Mu is the energy associated with exchange of particles, and mu dn is basically the work done either on or by the system when you have exchange of particles. So dW in some sense is traditional work done because of a certain force or energy exchange of some kind that is not heat exchange. Okay, so all of the energy exchanges. So for example, this phi dq term, for example, if you have charged particles, when we are talking about plasma would be in some electric field or magnetic field, and so there is going to be corresponding terms associated with the charged particles being in the electric field, right? So electric potential energy and the magnetic potential energy. And that's kind of what phi dq corresponds to. It's only the electric potential energy part, but you can write corresponding magnetic potential energy part in there, and that way you can always keep on adding terms into the first law depending on how many situations you need to deal with. So this is something you kind of need to wrap your mind around. That first law, as you studied in your undergraduate classes, dw plus dq is not the whole story. There are lots of missing terms which you need to find the right, and for example, for a rubber band, there is a TDL type term that can be added in there. So I will give you a little problem to work on later on that involves some rubber band thermodynamics. All right, so we talked about the state quantities. You can kind of categorize them into two buckets. One is extensive, meaning they depend on the size of the system. Intensive, that are inherent, they don't care about the size of the system. And those are there listed. SV and Q are extensive. Temperature, pressure, chemical potential, the electrostatic potential, they're intensive. And then we talked about the natural variables for U, which actually comes from the first law expression, du equal to TdS, dV, mu dN, because you have ds, dV, dN, SV, and N are kind of the natural variables for you. And once you have that, you can then define other thermodynamic potentials based on that by taking appropriate first order partial derivatives of the internal energy, right? Where is that coming from? Because you have S, V, N, and Q are the natural variables. You could take partial derivative of U with respect to S, partial derivative of U with respect to V, partial derivative of U with respect to N, partial derivative of U with respect to Q. So you have all of these partial derivatives that exist just because the dependence of the U on those variables. And each one of those have a name, and those names, those are basically new thermodynamic potentials that you can deal with. Or we can play with, and then they are also possess the same natural variables that U possesses at that stage, right? So that's kind of what you see there. You can rearrange the first law to get everything written in terms of ds, and then you can again carry out the same kind of analysis. S is now dependent on these set of variables, so you can look at the first order derivatives to get the next set of thermodynamic potentials, if you will, right? And you can get now very different relations than what you got in the case of U. There are, of course, various other thermodynamic potentials, and we will deal with most of them. Here, U, of course, is more prevalent, but free energy is useful. Enthalpy is very commonly used in chemistry analysis, and Gibbs free energy is the most useful one in statistical mechanics as well. In fact, depending on the ensemble that we use, the three names that I provided in the first day, the microcanonical, canonical, and grand canonical. They have their own conditions, but they have their own natural potentials as well. If you're doing, for example, grand canonical partition function, the grand canonical treatment of a certain thermodynamic system, you are going to get Gibbs free energy as your natural potential. And so if the ensembles are connected with a given potential, you need ability or mathematical tools to be able to translate those into other potentials. You need to, once you have G, you need to be able to calculate U, F, and H as well, right? Because a chemist may need H, and so you need to provide that. And that's the rest of the thermodynamic structure that we kind of looked at the other day. How do you transform from one to the other, right? And that is done through the legendary dual transformations. One example of that, already, is Lagrangian to Hamiltonian transformation. We will try to do a couple of problems of just simple mathematical functions and apply this legendary dual transformation today, so you develop some sort of a comfort level with them. And then once you have these differentials figured out for the thermodynamic potentials, you can use the analyticity, meaning those are well-behaved functions. So the second order partial derivatives of f with respect to, let's say, in the order u and s and t should be the same as, let's see, I think s and t are bad variables to choose from. Let's take t and v. So you have two variables. So you could take the partial derivative of f with respect to t first and then with respect to v, or you could change the order. And the changing the order should not change the value of the second order partial derivatives. And that gives you the Maxwell's relations that we are going to find very useful, right? So without going into all of the details, that's kind of what we did for different potentials. Refer to pages 6 to 9 from chapter 0 for more examples. We only looked at 2 here in the class, but they are all kind of the same in terms of the structure. So you will be able to follow and work through them independently. Then we looked at this mnemonic diagram that allows us to extract all of the potential. So I wasn't very clear on how the signs come. So let's take a look at the signs now. So let's, for example, let's take a look at the first relation, dv partial derivative of v with respect to x. That's the left edge in the diagram, because on the top left is v and at the top left bottom is s. And when they are connected, when you take partial derivative of v with respect to s, you can see that the thermodynamic quantity that has to stay constant, it starts with the first variable. So the v is connected with p diagonally, but it's connected with a negative sign. So actually what happens is, I'm going to correct this, there is a negative sign that comes here. So you need to keep p constant, but there's a negative sign coming because you're traversing that diagonal in the opposite direction. Okay, let me do it this way. That way it will look a little bigger for you. Okay, so there should be a negative sign here. Okay, and then let's take a look at so you looked at the left edge. Now let's take a look at the right edge. And if you now take a look at the top variable, derivative of that with respect to the bottom variable, partial t with respect to p, the quantity that you are going to keep constant is going to be, okay, so I think that I made an error there. That would be v. And in that process, you are traversing from p to v along the diagonal. And so if you're doing that, that sign, oh no, sorry, I made a mistake there. So we are doing the derivative of partial t with respect to p. You look at the variable in the numerator t, it is connected with s. So s would have to be hold constant. Okay, so s would have to be hold constant, but you are traversing in the direction that's opposite to the arrow. So there is a negative sign on this side as well. And that's how both the negative signs cancel, giving you the relation that I had written. Okay, so make sure you are comfortable with this. Okay, let's take a look at now the next one that I have written in blue, right, which is partial s with respect to p. So we're looking at the bottom edge, partial s with respect to p. S is connected with t, and you would have to traverse in the direction of the arrow. So the constant is t, and no, the sign would be plus, right? So plus over here, because s and t are directly connected. And now on the other edge, the top edge, the one that connects with s is phi. So you will write down partial v with respect to t. V is connected with p, but along the opposite direction of the arrow. And so you would need a negative sign there. Okay, so that's how this is negative, and this is the relation that we used in our example of expressing CV as a function of CP. Okay, so I hope all of that is kind of clear to all of you. I'm going to erase some of these arrows and stuff. Okay. Okay, that's how you figure out the signs. Does that make sense? Everybody with me? Now you would have to change the diagram. In this whole exercise, we were holding n constant. What if n is not constant and let's say s is constant? Then you would have to change the whole diagram. One of the vertices will become n, s would go away, and then you would have to figure out how it connects, and then you would get new set of Maxwell's relations. There are actually dozens of Maxwell's relations that you can find, and they are there in the notes, so you can take a look at them. But this diagram allows you to figure those things out. Yes, there is a question.
In the diagram.
Yeah.
The arrow for the first V and T is clockwise or anti-clockwise?
Okay, so the way I'm seeing it is not clockwise or anti-clockwise. What I'm looking at is, so which relation are you looking for? The one
in
in
the
the black or
in the diagram, in the diagram.
okay, let's take a look
If
at it.
yeah, I just
Yeah,
want to clear with
yeah,
that
in the
arrow.
diagram.
If I clear with that arrow, then there is no problem with the negative and positive sign, I guess, for me.
Right.
That's why.
Yeah. So the arrow goes from P to V and S to T. Are you able to see those?
P to V.
P to V, right? So this is the arrowhead,
Mm-hmm.
and then S
Is
to
V to
T.
T? Yeah,
No,
V to T
there are
and
no
V to
arrows.
S.
The edges have no arrows. Only these two diagonals have the arrows.
Okay, I get it.
Yeah. And if you're traversing in the direction of the arrow, like in the case for partial S with respect to P, the quantity that you hold constant is S connected to T. And so you hold, when you are holding S connected to T, S and T are in the direction of the arrow when you traverse S to T. Okay, so that's
Okay, thank you.
all right. That's good. Now let's move on to uh, the example that we looked at, right? Establish a relationship between CV and CP using quantities that are easy to measure. So we use some, uh, multivariable calculus and partial differentials to connect the two, CP and CV. And here is how it looks like. Equation C on the screen, CV equal to CP plus T times partial S with respect to P and partial P with respect to T. Both of these quantities are experimentally difficult to measure. And so how do you fix them? You figure out the uh, corresponding Maxwell's relations to translate them into derivatives that are measurable experimentally. And that's where you get the isobaric expansion coefficient, meaning how does the volume increase at constant pressure when you change the temperature? That's what alpha tells you, right? That's what number 2 is, partial derivative of V with respect to T, and that relates to partial S with respect to P, right? So an immeasurable derivative is connected with a measurable derivatives with the help of the Maxwell's relation. That's their power. That's what makes it powerful and interesting. And then same thing we did for partial P with respect to T. We use this again another partial derivative relation to figure that out. And it gave the interesting thing to note there is the minus sign in front. This is not how you would write things in the total derivative case. So let me write down a corresponding, I'm highlighting this expression here. If we had total derivatives that we were dealing with, right? So partial derivative of P with respect to T would be equal to, let's say we are writing it as dv with respect to dt divided by dv with respect to dp, and that would look like, right, it's just basically ratio dv over dt times dp over dv would be dp over dt, right? Everybody with me? Okay, this is with total derivatives. When you are dealing with partial derivatives, you get an extra negative sign. Okay, so don't get bothered by that. That extra negative sign is going to be there, and you can prove that. Also, I will add that to one of your assignments to prove that why these two relations are different. Okay, so that is something to note, and it's only in thermodynamics that you encounter these for the first time. So it's important to kind of note that that's not an error, that negative sign is necessary. So those ratios don't cancel. Okay, and so once we do that, we get Cp equal to Cv times the temperature, the volume, and then the alpha squared over K. And alpha squared over K, these you can read them off of tables because people have done experiments on any given species, and then they know the isobaric expansion coefficient or the compressibility. Compressibility is how does the system respond to pressure, right? So partial derivative P with respect to T essentially. So partial derivative of v rather with respect to p, that the denominator in the start expression, that's kappa v, and then partial derivative of v with respect to t, that's alpha v, and then v cancels and you get alpha over negative alpha over k, and then you add that in the expressions to get what you're looking for. Okay. Should be negative also. Right. Okay, so that's kind of just the review of what we did the first day. So if you missed the class, hopefully it's helpful. If you did not miss the class, still a review always is helpful. It kind of helps you find the big picture of things, which can get lost when we are going into the details. So here's the plan for today. We are of course done with 1, 2, and 3. We will do, oh, no, this is a new document, of course. So we're done with only one from here, review of thermodynamics. Today we will do, let's start with kinetic theory of an ideal gas, just to connect with the initial ideas of thermodynamics and what or the statistical mechanics rather, and what statistical mechanics entails. What we are going to do is not a first principle calculation. We are going to assume a lot of things which essentially become trivial, or they can be handled from first principles within the context of statistical mechanics. So this is not a statistical mechanical view of the ideal gas, but it's kind of intermediate. It's a step towards statistical mechanics. So think of that as a teaser or a motivation for the statistical mechanical investigations. And then we will look at concepts of probability and elementary statistics. And again, I have a pretty ambitious plan. I don't think we will go through all of them, but let's begin. So first thing we're going to do today is the kinetic theory of gases. And we will essentially heuristically derive the famous Maxwell-Boltzmann distribution that I'm sure all of you are already familiar with. Okay, so let's start. And again, make sure you stop me if nothing is making sense, or something is not clear, or if I make a mistake when I'm writing things down. Okay, so that's our plan. And this is one. Give me just a second. Okay, so what is our goal here is to understand the temperature as the average kinetic energy of the particles, energy of each particle, all of them added together for a gas. So we are taking a look at, so we take a gas of particles, of course, and each particle has the velocity with velocity denoted by a small letter v with a bar on top. And v, of course, is going to be a function of time. Right? So you can kind of see now we are worrying about the properties of individual particles. So that's kind of a departure from what thermodynamics normally does. They would be a function of at equilibrium state. On average, there will be always the same number of particles in a certain interval of velocity. Okay, so this is we want to look at now what happens at equilibrium. On average, so pay attention to the choice of words. The velocity of the particles is continuously changing. So if you take a look at, for example, the distribution of, let's say, the number of particles here at a certain velocity v, with a velocity velocity v on the x-axis. And then if you look at some kind of a distribution that doesn't have to have any specific shape at this point. But if you take a look at, for example, a tiny, I'm going to do this, a tiny section of this that has the width of, let's say, dv, right? Now, when I drew this graph, I am assuming v to be a scalar quantity, which is which is just one of the directions, but that's not true. We are looking at the three-dimensional velocity vector. And so what I'm going to say is this number, the area, the shaded, I'm going to actually also shade this area in a different color. So if I find this, that is essentially the shaded area equals the number of particles with v in the range let's call this, I'm just going to do some rearrangement. I'm going to write dv over here, and let's call the initial speed to be v0, and then the end of that interval is v0 plus dv, right? So in the range v0 plus dv. Okay, so that's what the shaded area denotes. Now, of course, we're jumping from one-dimensional discussion here to three-dimensionals. So the argument I'm making is, on average, at equilibrium, on average, the number of particles in a certain interval t cube v, this is how you would write a small volume element in a velocity space, right? In which is three-dimensional, would always be the same. Does that kind of make sense? At equilibrium, right? And on average, those two phrases are very, very important. Things are continuously changing. The particles are bombarding with each other, so that causes the velocity to change. But on average, in a given interval, you want it to be the same. You will expect it to be the same, even though individual particles are changing their velocity. So what we have to do is we find out what's the probability that a particle is in the interval d cube v. So now, because of this, we need to bring in probability, right? So probability of probability that a particle is in the interval t cube v, right? So we went from numbers, how many actually contains, to probability of an individual particle to be lying within that velocity interval. And so then we get a velocity distribution, kind of like I showed in the diagram there. And that velocity distribution does not change with time, right? So this allows us to think of that, we are questioning what is the probability, and eventually we get a probability distribution. Let's call it f of v. Again, it's the probability distribution, because you find the probability for each small interval over the whole range of the velocities that are possible within that gas. So probability distribution Okay, so lots of terms are coming up: probability distribution. After we go through this example, we will elaborate more on that, and we expect this probability distribution to be constant. They are rather independent of time. For equilibrium systems, we depart from equilibrium, it's not going to be constant, right? It's going to change with time. So we need all of this stuff. And so we're going to look at it. So our goal essentially is, if we wanted to uh, connect T with kinetic energy, but as an intermediate goal is to find this f of v. What is this probability distribution that we're going to find? So let's first start with writing the number of particles dn, and I'm writing dn because it's not the total number of particles; it's the number of particles in that small distribution. How do you get that? It's going to be proportional to n, because the larger the n, larger would be dn, right? So that's kind of obvious. It will also depend on the probability distribution at that speed v, f of v, whatever is the value of f of v, which is like if you look at the probability distribution here, it is going to be like uh, this dn is essentially the shaded region, which is area of a tiny rectangle, if you will. And the height of the rectangle is f of v, right? So this is the height. Sorry. So I'm going to write here is the height of the distribution times the width. The width in three-dimensional space is going to be d cube v. So everybody with me? Why you have this kind of a structure? Again, this is kind of coming from heuristic arguments, but you kind of have to understand what's going on.
Yeah.
So that's why it is connected with area, right? So area, because you have the total number of particles, then the height of the distribution, which line, along what position on the v axis we are looking at that tiny interval dv. If it's in the beginning, the height is going to be small, the number of particles is going to be small. If it's towards here, then if it's towards like near the peak, let's say, then it's going to be uh, having much larger number of particles. So that's what this dn signifies. Okay, and so we can then turn this around and then find f of v, which is the probability distribution. That means how many number of particles is the height as a function of v, right? It's basically this graph, but as a function of the velocity vector instead of just instead of the velocity. So it's just 1 over n d n over d cube v. Okay, now we may say, that looks weird. It does. We need to figure out what it's going to be. Okay. Now, what can we say about this probability distribution? First thing you can say is if you integrate over all the velocity values that the system can take, what do you expect this to be? So if you integrate f of v over dqv, what do you expect the answer to be? Total probability?
Yeah, we are integrating. That's why we are looking for the whole.
Right. So what would be the area under the curve for this whole distribution? So let me change my notation a little bit. I was looking at n of v here. Let's actually just look at probability distribution, or n of v. The units are arbitrary here on the y-axis. So I could say n of v looks like that or f of v looks like that. Either way is fine. What would be the area under the curve for the probability function? If that's a graph of f of v, what would be the total area under the curve? So think about it for a moment. There's no rush. Understanding these concepts is very crucial. And yes, anybody? Now, I have to warn you here that we are talking about continuous probability distribution. That's kind of, still, if we haven't talked about probability, it's a little difficult concept to grasp. We are familiar with the discrete probabilities, probability of getting a head when you toss a coin, probability of getting a 6 when you throw a die. That those are discrete probability scenarios. This is now a continuous probability distribution. There is a certain probability associated with having a speed v for the particle in this gas. So what is that integral going to be? Any thoughts? So what's the probability?
Integration is going to minus negative to plus negative, means there is
the whole range.
Total probability.
Right?
It's a total range, means probability going to be 1, but
okay.
For the area,
this is not ln. It should be ln n.
Can you say that again, Al Masood? I did not get that.
Ln n.
Log n. Ln
Yeah.
n.
Ln n.
Okay, so that's one answer that we got from Pradeep. We got 1. Any other answers? Anybody else has any thoughts? Okay, so let's take a little break. So think about the discrete probability. So that's why I said, it's little difficult to understand this continuous probability distribution. So let's take a simpler example. If you throw a die, right, and you have 6 possibilities, what's the probability of getting a 1 for when you throw a die? A 6-faced die?
1/6.
1/6, right? And what's the probability of getting a 2? 1/6, right?
1/6, yeah.
Okay. And now if you add all the possibilities, right, what we are doing when we're doing integration from 0 to infinity. So let's do a corresponding discrete case. So let me write it down instead of speaking. Sum over I equal to 1 to 6 pi is going to be 1/6 plus 1/6 plus 1/6
That is
plus
1.
1/6 plus 1/6. 1, 2, 3, 4, 5 is equal to 6, right? Or 6 times 1/6, which will be 1. So you just translate that into the continuous case. Now you don't have the discrete values 1 through 6, but you have continuous values. What would that integral be? When you go from discrete to continuous, integral summation becomes an integral. What do you expect the right-hand side to be? I want answer from all of you in the chat, so you can send me a chat. Just to me, you don't have to reply to everyone. So in the to everyone, just there is a little triangle, downward triangle. Click on that and select me in the list and send me an answer, 1 or 2. Right? You have these options here, 1 log of n and 2 is 1. Send me the answer. Let me know what you're thinking. Okay, I just received 1 response so far. I would like all of you to participate, so I know what you're thinking. Okay, very good. So we still have quite a bit of variation. I'm surprised. Okay, so we need to find out what's going on. Okay, I'm not looking for, okay, so all right. So there looks like there is still a confusion. I'm not looking for the actual answer. I'm looking for the option. So option 1 or option 2. Okay, there is a difference. Option 2 has a value 1. I'm not looking for the value. I'm looking for the option. Okay. So if you think you answered wrongly, you can correct. Okay, very good. That's that's good. That's good. Very good. So I'm happy with that now. That's very good. All right. So you understand what's going on here. All right. So let's now take it further. So I'm going to close the chat. So I'm not monitoring what your answers now. So now let's figure out the pressure, right? So pressure is going to be important to understand the velocity distribution, because that's going to tell us something about what's happening. So we're looking at, let's say, the walls of the container that I'm drawing here. And let's take a look at certain area over here. And we're looking at a specific direction, which is a z direction, to kind of keep things simpler for us. So that's the z direction, let's say. And we're looking at this much of an area. So if the particles have velocity v, let's take two of them, and they are okay. Now I can go back and label these as v. Both of them have the speed of, or the velocity of v, but it's directed like that. It's not directed along the z direction, right? And so the distance covered by the particles, which is denoted here, it's going to be vz dt. So the horizontal distance is vz dt, and because the velocity is at a certain angle, right? So now let's z-axis is perpendicular to the area A. So let me write down some of the important elements here. Z-axis is perpendicular to area A, and the momentum transfer by the particle, or let's say it should be from the particle to the wall. Let's do it this way. To the wall. Any thoughts? How much momentum is going to be transferred to the wall? So you have a particle that's coming in at an angle with the velocity of v. It hits the wall and it's going to bounce back, right? It's going to basically reflect, so it's going to go in a different direction. But we are only looking at the momentum transfer in the z direction. So what's the momentum transfer that's going to happen? Because it's the z direction speed that changes, right? It's not the other direction speed that changes. If it was going in the y direction, the y direction is not going to change, because A is only perpendicular to Z. Okay, so what's the change in momentum? The momentum transfer, P. Any thoughts? So let's say initially the momentum was M VZ, right? Let's see, it should be, this is, I will take the notation to be delta P, which is P final minus P initial. And initially the momentum was M. This is the momentum lost by the particle. So this is momentum lost by the particle, because the sign is going to be important. Right, so that's the initial momentum, mvz. What would be the final momentum? So it was in the z direction. Later on, after the collision, it's going to be in the negative z direction. So it's going to be negative mvz. And we are assuming elastic collision, so no energy loss. And so you get negative 2 mvz. And so that means the wall gains the momentum of 2 mvz. Everybody okay with that? And we call it P. Okay, so that's that. So there's a sign change. Momentum lost by the particle is a gain for that. Now the next question is, that's just one particle. We want to find out how many particles are going to hit the wall. How many particles with velocity we are going to hit the wall, hit the area A rather. We don't want all of the particles. We want just the ones that are going to hit the area A in time dt. Any thoughts? How would we go about calculating this? So if the speed is Vz, within that time interval dt, the particles are going to cover the distance of Vz times t. So if they are within that Vzt distance in time dt, they're going to hit the wall, right? Everybody makes sense? Everybody's with me on that? If they are within the distance along the z direction of Vz times dt, they're going to hit the wall in the next time interval dt. If they're outside of that, they're not going to hit the wall. Everybody with me on that? Does that make sense? Okay. So it's just going to be essentially the area of the parallel area of the okay, let me just write the answer to that, right? So how many particles are going to get? Or we don't, I'm not writing the number per se, but I'm writing how to calculate it, right? So all the particles inside a parallelepiped with basis area A and height VZDT, right? So think of the wall at the bottom, and so all of the particles that are within the VZDT distance are going to hit, and then it's not a rectangle; it's a parallelepiped because the particles are coming at an angle. Okay, and so it's essentially let me shade this area. Essentially, all of the particles within this yellow shaded region are going to be able to hit the wall at that area marked area A within the time duration of dt. Does that make sense? Everybody with me?
Yeah.
Okay. All right. So now next up. So we got that. All particles with velocity v, the travel. Okay. So let's now calculate. Oh, what did I do here? Next step for us to calculate the number of particles. So we want to calculate the number of particles with velocity v inside the parallelepiped so how do we calculate that, right? So let's call that number dn. It is equal to, it's going to be similar to the previous dn that we wrote down, n times fv times dqv, but we don't want all of them. We want only the ones within that little volume, right? The volume of the parallelepiped, right? So it's going to be n times dv over v. V is the total volume of the container, but we don't care about the total volume. We only care about the shaded area volume, right? And of course, this is three-dimensional, so that's why there is volume, even though it looks like the area in the shaded diagram. Okay, so everybody okay with this fraction? I will write down specifically what it means. And the rest of the part is the same as we wrote down earlier. F of n times fv times dqv is the number of particles with velocity v, but we don't need all of the particles in the container with velocity v. We only need a fraction of them that are sitting inside the parallelepiped. And so dv P
Dr. Kapale,
capital V. Yes,
could you please
Pradeep.
explain again for this?
Yeah,
For the
let me
DN?
write down. Give me a second
Okay.
to write down the definition of what I mean by dV over V, and then we will review that again. So it's a fraction of the total volume occupied by the parallelepiped, right? So what's a parallelepiped, right? It's a three-dimensional structure. I'm drawing it to be, I don't know, just something like that. So it's not square, the sides could be of different sides. And so that volume, all of those are going to hit the area. In the projected diagram here, area looks like a line. It's not, right? It has this other dimension that I haven't showed. So if, in your container, you will have, if you look at the earlier equation that we wrote down, this one here, right? dN is the number of particles with velocity v. Are you okay with that, Pradeep? That makes sense? The number of particles
Yeah.
with velocity v, right? Now
Yeah.
you don't want all of them. They are spread all over the container, right?
Yeah.
We don't need all of them. We just need the ones that are lying inside that parallelepiped. So in the next time interval dt, they have the chance of going and hitting the wall. Does that make sense?
Yeah.
Okay, and so that is going to be dV over V, right? So it's just our heuristic that it's going to look like dV over V. We need to calculate it. We haven't calculated it yet, but this is just our, let's say a symbolic description of what that would look like. So everybody okay with that so far?
Yeah, it's good. Thank you.
Okay, so let's calculate dV. dV is easy to calculate, right? So dV is going to be, it has the area A, because that's the base of the parallelepiped, right? And the height of the parallelepiped is Vz dt. So if you know the area of the base and then the height, even if it's kind of tilted, it doesn't matter. You can calculate the volume. So that's very easy. And each one transfers the momentum to mvz, right? So then we can multiply. So the impulse, you can calculate the impulse per area A is going to be the total force dF applied within the time interval dt is going to be the change in the momentum 2mvz that's imparted to the wall times the number of particles, right? So you have n number of particles, each one giving the 2mvz impulse to the within the time interval dt to the wall. And so dfa dt is how we are representing that. And so we are now able in the position to write down everything here. So it's going to be 2 nm Vz squared, because dV contains Vz, and then f of V d cube V times A dt over V, right? V is the total volume, so we don't need to calculate that. A times Vz times dt comes from the dV, and then the rest of the expression. So we have just basically connected dN and dV expressions and added them together. dt is there on both the sides, so we don't need to worry about that. We can remove that. This is basically the force in a time interval dt. Okay, so now if I want to calculate the total pressure, is going to be 1 over the area times the dF, the force exerted on the area A, right? So that's all there is to it. So we can then do the integral A over V, integral now negative infinity to infinity, because on the right hand side it's the integral over dV. And we can now split the integrals of the x velocity, y velocity, and z velocity to make our life a little easier.
Yeah.
And then for z, we only take 0 to infinity. Why? Any thoughts on why that should be the case? Because vz needs to be in a certain direction. If vz is directed opposite from the wall, it's not going to contribute to the pressure on the wall or the force on the wall. So that's why this integral is important, the limit here. Okay.
Dr. Kapale, we left the a over here, or 1 by a?
1 by a is it's gone, right? Because there is a on here. We divide by a, that a will be cancelled, right?
Okay,
The a is already there, so a goes away. Okay. Okay, now another thing to kind of note some of the properties here that we are assuming. Again, we are bringing in lots of heuristics here, not assumptions per se, but heuristics, meaning, you know, those are kind of guesses, right? Educated guesses. Since the gas is at rest, that means f of v must be independent of the direction of v. Right? It doesn't matter whether v is going up or down or left or right. F of v should not depend on that. It should be exactly the same. And so what we are going to get is, so f of v would be proportional to the magnitude of v, not the direction. And so we can write down integral 0 to infinity dvz that we need to evaluate as half of integral negative infinity to infinity of dvz, right? That's clear. And so then P times the volume is going to be M times the N. So we just took the M out. The 2 is gone because of this half. So what I'm basically doing is we are making all of the 3 integrals from minus infinity to infinity, and the half cancels. So the 2 that we have there, and then we do the integral negative infinity to infinity, p cube v f of v vz squared. Okay, everybody with me? So then the whole integral is vz squared, and we need to calculate this integral now. We can write this down as, so by looking at the nature of this, in statistics, when you're basically multiplying some quantity by a probability distribution and then doing the integral over all values that the system can take, that is denoted as the average. So this is average of v squared. Sorry, I did not write that correctly. It should be average of v squared. Everybody with me on that? Okay. Okay, that's just the definition. That's how you write down. It's a notational thing, and this value in this particular case, because of the directional independence, it would be the same as vy squared or vx squared. They all would have exactly the same value. And also because we now know, or we know v squared is equal to vx squared plus vy squared plus vz squared. Vz squared is going to be 1/3 of v squared. We're just basically trying to simplify the integral, okay, with the help of something called the Gaussian integral idea. Okay, so Vx squared. I'm just writing everything down. Vy squared plus Vz squared. Okay. So then we get the pressure times the volume is equal to m times n times 1/3 of V squared. And so let's take a look at this. That means what we have is half m V squared times 2/3 times n, right? So I'm just rewriting this. That means it's equal to 2/3 n times the average kinetic energy. And so that means Ke just means the average kinetic energy. Everybody with me so far? Does that make sense? So we kind of proved, in some sense, the ideal gas law in this form, that the pressure times volume is equal to 2/3 of the number of particles times the kinetic energy. Now, of course, let's connect that with n kBt. So that's the ideal gas law. And if that's the case, then n cancels. You get the temperature is equal to, well, actually, we don't want to do it that way. I want to write down, so 2/3 n times the average kinetic energy is equal to n kBt. That means the average kinetic energy is equal to 3/2 of kBt. So we proved using microscopic considerations, looking at the velocities of all the particles and their distribution, and without assuming any specific form for the velocity distribution. Remember, I never wrote down what is the functional form of f as a function of v. We did not have to write down. We only made some small assumptions that it does not depend on the direction, whether you're looking up or down or here, there, doesn't matter. That means all three components, x, y, z, vx, vy, vz, are equivalent. That means their average speeds, average vx squared would be the same as average of vy squared and vz squared. That's the only assumption. And after that, we get the average kinetic energy equal to 3/2 kT. This is called the equipartition theorem. And we kind of take it for granted in thermodynamics, but it can be proved using the microscopic considerations. And another thing that is important here is, even though we did this calculation for an ideal gas, the equipartition theorem actually happens to be more general. But our theory is not more general. That's why we can only right now say that it only applies to ideal gas, but it actually applies even beyond that, right? So everybody with me so far? Does that make sense? Let's now take it's 10:35, so take a 5-minute break. Let's come back at 10:40, and then we will do the next topic, which is actually calculating f of v, right? So we need to calculate that, see how it looks like, what form it takes, and so on. Okay, so I'm going to stop sharing. All right, so we are going to now continue this discussion and determine the shape of this function f of v, right? So far, we only looked at simple physical arguments to understand some of its properties, but we did not look at the actual shape. So now we are going to do that. So first thing to know is, and this is called the Maxwell velocity distribution. So I'm going to title it Maxwell velocity distribution. So that's our topic. So we have seen that it's the function has to be a function of v or v squared. And what we are going to do, instead of finding f of v, we're going to do f of v squared eventually. So remember, the gas is isotropic. That means gas is more or less uniform in all direction. That means f of v vector is a function of v magnitude or v squared. So we are going to look at f of v squared instead of f of vx, vy, vz, right? Or what also it means is f of vx squared plus vy squared plus vz squared, which is essentially f of v squared, is going to be f of vx squared. The x, y, z components can be separated out. There is no interdependence of them. So x vy squared and f of vz squared. Okay, so they are independent of each other. And so all we need to do is find one of them, and then we have found all of them. Okay, and so what is f of v? Let's write down explicitly what we are what it is, and it's f of v squared rather is the probability density. When you have continuous distribution, the term is not probability. The actual correct term to use is probability density of finding a particle with velocity v, and this has to be proportional to the product of the probability densities of finding the particle at speed vx, vy, and vz, as long as these are statistically independent, right? So we are assuming vx, vy, vz are statistically independent. So this needs to be equal to the product of vx squared times vy squared vz squared. So a function of vx squared plus vy squared plus vz squared that splits into product form can only happen for an exponential function. That means f of v squared is going to be some constant c times exponent of a times v squared. Only the exponential function like f of v squared equal to c has the correct form to satisfy, let's call it equation 1. Would you agree with that? Let's say we take a logarithmic function. For logarithmic function, the product becomes a summation. For exponential functions, the summation becomes a product, right? Summation of the argument is a product. And so that's kind of obvious. So we know that's how it's going to be. That's a mathematical heuristics, but it's useful. We also want the function to be normalizable. F of v squared needs to be normalizable. That means there will be a constant in front, c. That c is the normalization constant. And that means integral of minus infinity from minus infinity to infinity of dvi f of vi would be equal to c, which is equal to negative infinity to infinity dvi exponent of negative a vi squared. Because it's normalizable, a has to be less than 0, right? Because otherwise it will be exponentially growing function, and a function that keeps on growing exponentially is useless. It's not going to be physically meaningful. And so that's what we get from normalizability. And that's why we have this negative sign here, okay? And so this is now a Gaussian function. Of the velocity component, and c is determined from this integral. And so once you do the integral, the value of the integral is known to be square root of pi over a. That's a Gaussian integral. You can use Mathematica, for example, to figure that out. We will do some simple Gaussian integral treatment later on. So for now, just take my word for the value. And so c will have to be square root of a over pi. Okay, so that is determined. We have determined that a needs to be negative, and we have determined the value of c. And then we know now from the kinetic energy expression is going to be equal to 3/2 kT equal to the average kinetic energy. And so if you do just one particular component mvz squared, that's going to be equal to kT, right? Because it's not the whole kinetic energy half mvz squared. We are removing the factor of 2, and so you get kT equal to mvz squared. Is everybody okay with that? This is just based on the equipartition theorem. By the way, I did not comment on the equipartition theorem. It is a very powerful statement. It tells you not just something about the kinetic energy, but actually it goes beyond that. It goes and applies to all of the degrees of freedom. That means the average energy contained in a given degree of freedom will be 3/2 kT. So it is even more general and more powerful than what we have already seen. And so this means this integral is going to be d cube v f of v vz squared. Okay. And so when we know that, we can then figure out some other properties of the okay, so I'm just going to now work with this integral. So just separate out the x, y, and z component. Vx squared minus infinity to infinity dvy f of vy squared minus infinity to infinity dvz vz squared f of vz squared. Okay, everybody with me? Only this integral is different because of the z component. The x and y integrals are exactly the same. And so then we can write this down. What would be the value of these integrals? Any thoughts? Any thoughts on those? It's essentially normalization along the x direction and the y direction is going to be 1, right? This will be 1, that will be 1. So you only need to worry about the z integral. It's going to be m negative infinity to infinity dvz f of vz times vz squared. And now we're going to substitute for the f of vz, which had the normalization of a over pi square root of that integral minus infinity to infinity dvz, and then we had exponent of minus a vz squared vz squared. Okay, so that's just the average value of vz squared. Now we can do the integral. Because the symmetry, you can get 2 outside and change the integral from 0 to infinity instead of negative infinity to infinity. So we're only worrying about the positive values and just double the value of the integral, exponent of minus a vz squared. And that gives us okay, so how to do this integral? You just substitute x is equal to a vz squared, and dvz is going to be 1 over 2 root a times dx over root x. So just helping you with one of the Gaussian integrals. This kind of integral can be done using Feynman's method, which uses derivatives, but we will work on that later. That will be kind of a mathematical primer we will look at later. So this part is all same, and then we have the value of the integral. This 2 root a will just come out, and then because there should also be one more a, because x squared a vz squared, yeah, we will need extra a because vz squared is equal to x over a, and so you will have here 2 times a root a, and then you are left with the rest of the integral 0 to infinity. Because of the change of variable, now it's a dx integral e to the minus x, and vz squared, hold on just a second, would be, yeah, vz squared is x over a. That doesn't make sense. Oh, but there is also square root x coming from there. So dx, you're left with square root of x. Right. So let's see where that is coming from. Okay, so I'm just going to add something here. dvz times vz squared would be equal to 1 over 2 root a dx, where square root of x times vz squared would be x over a, and so that gives us 1 over 2a root a square root of x dx. Okay, and that's what I have used in writing down this integral. And that type of integral can be solved using a gamma function. So let's do a little digression. Let's call it a mathematical
Kapale,
note.
can you go to the above, please?
Yes.
Thank you.
Yeah, so it's just a change of variable. So let's take a look at a mathematical note. Let's look at something called a gamma function. Which is defined as gamma of z equal to 0 to infinity dx e to the minus x, x to the power z minus 1. Okay. And then there are some interesting properties of the gamma function. So you could see the integral that we are trying to do is x to the power half, right? So here we have, this is essentially equal to x to the power half. And if half is equal to z minus 1, then that gives us z equal to 1 plus a half. So it's 3 halves. Right. Okay. And so we will need to calculate gamma of 3 halves essentially. But you don't always have to do the integral. Gamma function has been studied in quite a bit of details. And here are some important properties of the gamma function. It turns out gamma of half is equal to square root of pi. And once you know that value, you can actually calculate all of the other ones. And gamma of 1 is equal to 1. So with these, and then there is a recursion formula, you can basically determine gamma of any value. So z plus 1, gamma of z plus 1 is z times gamma of z. So you could sort of see this is similar to a factorial function, but it's more general. It applies to continuous variables as well. In a factorial, let's say factor n plus 1 factorial is equal to n times n factorial. This is gamma of n would be, sorry, n1 plus factorial is, the way it works is, I'm trying to connect them, but you can kind of see the nature, right?
That one is the
Argument,
formula.
right? Z plus 1 gamma is equal to z times gamma of z.
Gamma
Same
z.
thing. N plus 1 factorial is equal to n times n factorial. So it has kind of similar structure to the function. So there is similarity.
We try to show gamma as a factorial.
It's similar to factorial function, but you define factorials of only integers. Gamma function is defined for real numbers as well, right? Okay. And we will look at the correspondence of the gamma function with the factorial function later on. We need that as well for most of this. So with this, you can calculate you can essentially directly substitute the values of these integrals with the help of the gamma function. So like I said here, z is equal to 3/2. So we basically need gamma of 3/2, which is going to be equal to 1/2 times gamma of half, right? Because 3/2 is half plus 1. And so it's going to be z, gamma z, which is that. And it is going to be square root of pi over 2, because gamma of half is given. So these are given. Right? You can prove them, but for now, we're just going to assume them. And so that's the value. That means the integral that we were dealing with was kt is going to be m. And then we had 2 would be canceled, right? These 2 I haven't canceled, but they can get canceled. So m square root of a over pi, and square root of a would cancel. So we did not do that cancellation. So we are essentially left with m times 1 over a times root of pi. So that's just the simplification of the 2 terms before the integral. And the integral itself is gamma of 3 over 2, which is equal to half. Root pi would cancel, and you are just left with m over a. Pi over 2. Yeah, half comes from there. So it's basically that, and root pi cancels. So m over a. This implies what a would be. Now, because remember, we assumed a certain form for the distribution, and we determined the normalization coefficient, but we had to determine k. And so it turns out to be m over 2 kt. And that means the velocity distribution vi is going to be square root of a over pi, which is the normalization constant, times exponent of minus a vi squared would now look like square root of a is m over 2 kt. Where is the square root? Yeah, square root of a over pi. So you will need m over 2 pi kt by substituting a, exponent of minus m vi squared over 2 kt. Okay, everybody with me so far? So just based on the standard arguments, we have figured out the velocity distribution which is called Maxwell's velocity distribution, because he took Maxwell historically speaking. What Maxwell did was he was motivated by Boltzmann's work, and he looked at the kinetic theory in more details. Essentially the microscopic interpretation or microscopic viewpoint on thermodynamics, and he was the first one to derive the Maxwell-Boltzmann distribution. And Boltzmann, because you have Keith in there. Thomas, you had a question?
Yes, I noticed that one of your equations you put up there about in the middle of the page, you put above that, you said that n+1 factorial equals, should be n+1 times n.
Right. It should be n+1. You got it. Very good. Thank you. Okay. Yeah. Okay. Now I can connect this very easily. So what happens here is I'm going to try to slightly write it differently. So n+1 factorial is actually gamma of n is going to be equal to okay, let's not try to do that. We'll work on the gamma functions a little bit more later, and at that time we can write it. Hold on just a second. Let me just find it out so that I don't make any mistake there, and then we can. It's one or the other, so that's why I kind of get confuse myself sometimes. Yeah, it's n-1. Okay, so yeah, that's what I confuse myself with that. So let's go back to where you guys are. Okay, so the correspondence is gamma of n is equal to n-1 factorial, right? So what you have here if it is n+1 factorial, you subtract, you add 1 to it. And so this is gamma of n+2 equals to n+1 times gamma of n+1. Yeah, okay. So that's the corresponding factorial relation with what I wrote down here. These two things are completely identical. Okay, and that's the relation between gamma of n is n-1 factorial. So gamma of 1 is equal to basically 0 factorial. That's why it is 1, right? We know that already, that 0 factor is 1. So we have now been able to establish the Maxwell-Boltzmann velocity distribution. So okay, so that's what we just proved. I'm going to right. So the next topic is probability, and then I will try to go through things very quickly. And we have to stop a little early today. I have a meeting at 12, so we will stop around 11:55 or so. But let's see how much we can get done. Okay, and in terms of the concepts, there is really nothing new. All of you are familiar with the the concepts of probability. And so I'm just going to quickly run through them, right? So the first thing that we are going to talk about is the classical probability.
Dr. Kapale, I think you didn't share.
The screen.
Yeah, I need to share the screen with you, right? So let's do that. Yeah, I haven't done anything yet. Okay, are you able to see? Yeah, you should be able to see now. And all that we are going to do is just quickly review the concepts of probability. And so first one is the classical probability. And this is not classical in classical mechanics, right? It is a term that's the standard kind of definition. So for, let's say you have something called a sample space. Okay, so it's a set that contains all possibilities, all possible outcomes of an experiment. And we call, that's a sample space. And what you need is not the whole sample space, but you actually need the length of the sample space. So the length of the sample space, we call it W. And then the probability of an experimental outcome, probability of a certain experimental outcome of a certain is going to be the number of expected values divided by W, right? That's what it is. So for example, if we do a coin toss and expect head, because let's say it's a game where you get to do a certain thing if you get heads, and you don't get to do it if you get tails. So you get to serve, let's say in a game of tennis, if you get the heads, right? Who is going to serve first? They do a coin toss to figure that out. So what's the probability? What's the sample space? So first write down the sample space is essentially just head and tail for the coin toss. The W is going to be 2, and the probability of getting head is going to be 1/2. Everybody with me? Okay, so that's just kind of defining everything, sample space and everything. Now, let's say we do n coin tosses, and expect. So we are trying to look at maybe a statistics of a tennis player. How many times in n games did he get to serve, right? So if he wants to serve all the time, he wants to be a lucky tennis player, he wants to be serving all the time in all the games. So we expect heads. N heads. What's the probability of getting n heads? Any thoughts? How would you write that? You can unmute yourself and quickly give me the answer.
I think that one is 1/2.
You think still 1/2?
Because
Anybody?
there is a probability the head and tail only 2. There are only 2. outcomes.
Right, but we have n coin tosses. So you do the first one, and we assume that the coin tosses are independent. So you do the first coin toss, the probability is half of getting heads. The second coin toss, probability of getting heads is still half. Then the third one, still half, all the way up to n turns, right?
Yeah, 2 to the
And so
1
it's
by
going
2
to
to
be
the
1
power
over 2 to the
to the
power n. Is
n.
going to,
Yeah.
so for independent events, the probabilities are multiplicative. You need to multiply, right? So this is because we assumed the consecutive or the individual coin tosses, all coin tosses are independent of each other, right? So that's the classical definition of probability. It comes from, what's the length of the sample space and how many of the events are of interest to you at that. So it requires a lot of counting, right? So it requires counting methods to make the task easier. That's one way of figuring out the probabilities, actually counting how many things are there. It may not always be easy, right? So, but that's so what happens in connection of this with statistical mechanics. In statistical mechanics, we assume that all accessible states or microstates of the system are equally likely. Yeah, this is called, so if there are W outcomes, then the probability is going to be 1 over W when you count the number of microstates. Okay, so that's going to come when we start looking at the microcanonical ensemble. And this is called the ergodic hypothesis. We assume all of the microstates are equally likely, right? So that's how the process kind of works. You can determine probability by doing experiments as well, and that is the concept of statistical probability. So this is what we are going to do now. Let's take a look at okay, so what is statistical probability? What you do is we carry out experiments to assign the values of the probability, right? So for example, a coin that somebody gave you to do a coin toss may not be a fair coin, right? And so then if you toss it every time, for some reason, it gives you more heads than tails. And so you can't say the probability that you normally assume. You can't assume it to be fair, and you can't assume the probability of getting heads would be always half. That may not be the case. In that case, how do you determine the probability? So the phenomena that you are not very familiar with, you try to find the probability by doing experimentation. Let's say you want to find out what's the probability of having a person the height of 6 feet from a certain population sample. You can't figure that out on your own, right? There is no simple classical probability type definition to figure out the probability of such a scenario. So the only way you are going to do that is doing by experiments, right? So you are going to measure maybe 100 people, ask them what their height is, and then you're going to write down, and then that you're going to try to figure out the probability of that event from that. So are 100 events enough, right? What should be the sample size so you get the probability correct? And so the way you do the statistical probability is, so let me write down a statement here that illustrates this. It says, okay, so what we do is, suppose, let's take a physics example. Suppose we have a sample, a radioactive sample, that decays and we measure the counts with the help of a Geiger counter. Let's say in a 10-second interval. Okay, so that's just kind of so we get total, we get n trials, so total n trials, and let's say ni is the number of times the decay happens. Okay, so you get, you are looking at a 10-second interval, you do the experiment, your Geiger counter is open for 10 seconds, you count how many decays you got, and then you do it again, and you do it like n times. So then the relative frequencies which is the ratio, let's say ni over n, is constant as n goes to infinity. As the number of trials increase, number of times you carry out the experiment, the ratio ni over n tends to be constant, and then the value of the probability pi is going to be limit n going to infinity ni over n. Okay, so it's a limit n going to infinity. That means you need to carry out extremely large number of experiments to be able to figure out the statistical probability. That's kind of what happens in quantum mechanics also. When you're measuring a quantum system, you need to do many experiments to figure out what the experimental results are. Without that, you're not going to be able to figure things out. Figure out the probabilities. And so to kind of illustrate this, let us do a couple of experiments with this. And then we will look at the remaining concepts of probability. The simple, how do you calculate the probabilities of compound events? How do you count the events, the permutations and combinations? That's mathematics you have already studied. So I'm going to give you a little copy of a chapter from one of the books to read through. And so there's going to be a little reading exercise for you, and you will be able to figure out some of those concepts. I won't be going through all of the details, but what we want to do today is in the remaining time, carry out some experiments of our own using computer to figure out these probability distributions. Okay, so what I'm going to do now is go to the class page on Western Online. Okay, so let me share that screen with you. Should be the one. Okay, so we go to the lecture notes section. If it will let me, probably ask me to log in. Okay, here we are. So let's go to the lecture notes sections. If you go to the, let's actually go to the home. Oh, sorry. Give me just a second. Okay, I'm going to change my role as the demo student, so we will also be able to verify that you are able to see it. Go to the lecture notes and videos section, go to the mathematical necessities, and there is a probability statistics extra reading. That is your reading exercise. And if you after you read through that, solving the first homework would be straightforward. So make sure you read through that. I basically just gave you the two definitions. Now what we are going to do is I'm going to stop sharing this, and we are going to create a new document here, and let me share this screen with you so you can see from the beginning to the end how I'm doing this, and you should be able to do this on your own as well. So I'm here on a new window, which will, okay, so I need to keep this accessible, and I need to go here. Okay, so what we are going to do is in Google, I'm just going to search COLAB. You can write down the steps somewhere, or you could try to simultaneously do it on your computer as well, right? So it goes to welcome to Collaboratory, the first research result here. We click on that, and then it opens up my account. It already knows the stuff that I have done. And so what we're going to do actually is cancel. I'm just at the bottom of the window. It says new notebook. I'm going to create a new notebook. Okay. And we do a experiment on, let's name it coin toss. Okay. So we're going to now try to use the computer to do coin toss experiments. So we need to be able to generate random numbers for that. And so in Python, there are different packages that you need to be able to do certain kind of computations. So you need to first load those packages. And so one of the important packages is called NumPy. It's a numerical routines. And one of the formats is import numpy as np, so it gives it a shorter name, so it's easier to kind of deal with. If you haven't played with Python, you can kind of try to do this along with me, or you can just watch me and then I will share the file with you later. Either way works, whatever is comfortable for you. After we are done with this, we also want to plot the graphs. So I'm going to say import, and there is another mathematical plot library that Python provides. So we need to load that as well. So it's matplotlib pyplot, and I'm going to call it as PLT. So just a short name for that. And then we also would like to calculate some statistics. So I'm going to use I think let's not do the statistics part right now. We will do that part later, right? So we will worry about that later. For now, we want to keep things simple. And let's say, so those things are there. In Colab, you can also add text and stuff. So I think I need to move this up if it will let me. I haven't played with this text part. So let's just write down. Oh, what happened? Everything okay? Okay, I just wrote some text so that we can, and then now we need to, okay. So we can try to set up that. So we want to first find out what is our sample size. And let's start with 100. We can always change that later. And what I'm going to do is all the results that I obtain, I'm going to store them in an array. So I need to set up the array, which initially is going to be populated with zeros. So zeros of the sample size. So if our experiment needs, if it is done 100 times, I want to store the results of the experiment 100 times in an array. So I just created an array. Now let's carry out the experiment. So for I in range of sample size. So that means this just tells it carry out the experiment sample size number of times. And what do we do in the experiment? We save the result of the experiment. And what is the experiment? We want to generate a random number. So this numpy has a random function. And we want to generate a head or tail, right? So these are two possibilities. Let's call head as 0, tail as 1. So you just basically need to create a random number that's either 0 or 1, right? As simple as that. And so we just do that is done by using a random integer, randint, that's the function for that. And we want the random integer to be between 0 and 1, right? Okay, and let's see if it does that. So we just let's just print n of I every time that number is generated. Let's print it and then let's get out of it and let's see if it actually does that or not, right? So plotting and stuff we will do later. So let's start with a sample size of 100. Okay. Sorry, 10. So smaller so that when we are printing it, we will know that it's doing things correctly, because you don't want to really print 100 numbers. That's a whole lot. So I go up here, make sure I execute. So there is a little play button here. You have to execute that, and that just the Google servers in the back end carry out all of the processes. And so we did that. Now let's do the sample size part. And you can see it just gives me 0. So something is wrong. It's not really doing what it is supposed to. So it is giving me floats. It's not giving me integers. And so something is not correct. So we need to figure out what's happening. Well, let's try 0 and 2. Sometimes the way these things work is in Python, the second integer. Okay, this works 1 0 1 0. It's giving us 1 and 0, and it's giving us a real number. We don't need a float, so I'm going to convert that into an integer, and let's print that again. That didn't do anything. So I think it's probably the print function that converts it into that. So that's okay. All right. So when I do np random integer 0 to 2, it is able to generate 0 and 1, not 2. It excludes the last element. That's why it needs to be 0 to 2 to generate two numbers. So you can see it generates 1 and 0, 1 and 0, 1 and 0. Now from here, if you do a sample size of 100 or 1,000 or million, if you look at each individual entry, that is very cumbersome to count, right? We don't want that. What we want is counting the answers that we are getting. So instead of printing, let's now do something with what we have, right? So let's plot it, right? We can plot it, and by plotting, we will be able to see what's going on. So we're going to plot the numbers directly. First thing that we're going to do is plot the numbers directly. So you do PLT. We already called the function. We ask it to plot what. It can plot the whole array. And so we plot the whole array, and so we like that. And then let's give our plot some labels. So x label is going to be experiments, right? So each individual experiment, and the y label. So you can see it gives us the clues. So y label, so we don't need to really remember syntax of everything. It helps you quite a bit there. And n is the value that we obtained. And then we just say show the plot. We can even give it a title. So let's give the plot a title. We can say coin toss experiments, number of trials is equal to, let's say, n, the sample size. Yeah, I think it's not going to like that. Sorry.
Double, yes.
Okay. Okay, I'm just using some little trickery here. Because the sample size is a numerical value, I'm converting that into the string and adding that into the plot title function. I hope that works. If it doesn't, it will give us some error. Okay, it didn't like it. So what we need to do is how to convert the integer into the string in Python. So I'm just going to go here. Are you able to see my other window, the Google window? I'm doing a search. Okay, so that's good.
Yeah.
What we need to do is convert integer to string. So this is how you can quickly look for help. And str should have worked. So, but the trouble I think is we need to generate the string outside. Okay, so we will just do that here. Equal to str of the sample size. Okay, and then we add that string in here. Okay, hopefully that will work. It may not like string, so let's give it something else. So str ss, so sample size. Let's see if that part works. No, it doesn't like that again. I think that it doesn't like that the string in the title is weird. So here is a way to do that. We just call it title string is equal to coin toss, so experiment with number of trials dotted with this, and then here we just put okay. So what I did was I defined the title outside of the plot title and then just passed it as an argument to plot title, and that should work. It still doesn't like this dot operator, so that should have worked. It's string concatenation operator. Okay, they wanted plus. Okay, so we can do plus. Yeah.
Here is a
Okay.
dot after experiments. Maybe the dot will be number.
Yeah,
after
no,
number.
that dot is fine. Coin toss experiments. Okay, we just do that. That's inside the string, so that shouldn't matter. Let's see, this one will probably work. Okay, so it works. And these are our trials. So you can see first trial was 1, then you got 2 zeros, then 1, then again another 2 zeros. No, here we got 3 zeros, then 1, then 2 zeros, and then 1, 1, 1, 3 ones, right? So again, it's kind of random, but we don't know how many times are we getting the zeros and ones. So what we need to do is we need to actually calculate the frequency. How many zeros out of 10 trials and how many ones, right? That will kind of tell us more. And so we can get the Python to do that. So here we are saying print, or rather plot. Okay, that's what we did there. Plot the numbers directly. And now we plot the distribution. So let's plot the histogram. Okay. And so the matplotlib library also has functions to plot histograms. So what we need to do is first, I'm going to generate certain arguments that I know are helpful. So I'm just copying this part here. Certain arguments that tell you dictionary of density equal to true, the colors I'm choosing to be blue, alignment, and alpha is just the how deep the color is, right? So those are just standard kind of beautifying arguments you can put together. I put together them as in a list, and I'm going to write down the function here. So plot histogram, right, takes the data, which is n. It generates 16 bins. We can change the bins to, in this case, I think maybe 10 would be enough, because we basically have only two, right? 0 and 1. And then the range is going to be 0.5 to 1.5, right? Because you have, now let's see, the range should be 0 to 1. Let's keep it that way, because our data is between 0 and 1. And then the rest of the arguments are passed to the plot histogram function, okay? And then the values that it gives you the x, that means the frequency per bin. And bin means, if you have, let's say you have a range 0 to 10, you could decide the bins to be, first bin should be 0 to 1. So if the number lies between 0 to 1, that will be the first bin. So it's taking the balls and putting in the buckets, right? So the bins are just buckets. And for coin toss, you only need 2 buckets, right? So 2 buckets are decided, and patches is some other argument that it gives. We don't need to worry about all of that. And what we need to do now is add new labels to the plots, and then show how it looks, right? So I just wrote plot y label equal to counts, x label is data, and then show the plot. So now we should get 2 plots, which first one gives us the exact trials, and then the next one puts them into the 2 bins, right? First bin, the bin of the 0 to 0.1, and the other one is 0.9 to 1. Though here the bin size is not really important for us, right? So does that make sense? Now, does that look like a fair coin? Okay, 0 is heads and 1 is tails. So it gives you tails more times than heads, right? So right now it doesn't look like fair coin, but is that happening because we did not toss it long enough? Or is it just an unfair coin? You don't quite know unless you do the experiment a large number of times, right? And that's what we mean by experimenting large number. So I'm going to now go from sample size 10 to 100, and let's see what happens. You get all of these things, that plot is going to become essentially useless after a while. But out of 100 tiles, yeah, it's plotting the density is true. So I'm going to make density equal to false. So it will actually give us actual counts. And let's run it again. Okay. So out of 100, we got 50 heads and 50 tails. So that sounds like a fair coin. So that means to figure out the probability in these kinds of situations, you need to run the experiment a large number of times. Now, it's kind of nice that with 50 trials, we already got the thing. Sometimes even that doesn't happen. Sometimes you won't get. So like, I ran the experiment again. Now I got slightly more heads than tails. So it's not quite balanced. So it hasn't quite reached that limit. Remember, limit is n going to infinity. N equal to 100 is not infinity. It's extremely small. So now I'm going to make it really large. Let's make it maybe 10,000. And let's run that experiment again. And for 10,000, now it's almost 5,000. It's slightly less than 5,000 and slightly larger than that. Now with this, it's very difficult to see that, and that's why I had the density equal to true. So what it does is it kind of normalizes it. It does not give you the actual count. It normalizes it. What am I doing? Okay, so let's run that again. And it just gives 5, 5, right? So again, it looks like, so it's just
Different.
some arbitrary count, but it looks like they're slightly different. This one is still slightly lower. So even with 10,000, it doesn't work. So let's make it 100,000. Let's run the experiment again. And this part is not giving you anything because it's just going up and back and forth. It looks like the whole area is covered. But you can see this is now pretty close. The difference is very small. So the difference is approaching a certain value. And if we go now to 1,000,000, we will see that that difference between those two bars would be even smaller. As it runs and does the calculation, you can see now they're even closer, right? So as n goes to infinity, it's approaching a half and half value, right? Equal heights, meaning the equal probabilities. Does that make sense? Everybody with me? All right, so that's a good experiment. What I'm going to do is now make a new notebook, and we're going to do exactly the same thing, but instead of coin toss, let's do a die throw, right? So we have a die, let's say that we're going to throw, and what I'm going to do is copy everything from the coin toss experiment just as it is, so that, and I'm going to call this a okay, so we're going to throw multiple dice, and let's now add the rest of the commands. I'm just going to copy everything from there. The whole structure works, is useful. So only thing that changes is the random numbers that we generate. We don't want to generate integers between 0 and 2 now. We want to generate the lowest value is 1. The highest value is going to be 6. For Python, you need to put 7. That's just the way it works. Because it's a mute, it's a the higher value is excluded kind of a cell. It's an open interval. And so it's 0, 1, 7. It's closed on the lower side, but open on the upper side. That's why you have to do 1 to 7 instead of 1 to 6. Let's do the sample size of maybe 10 and then print the values to see what it is doing. Okay, so let's print it and let's run. Okay, so you can see it generates 1, 3, 5, 3, 6, 4, 6, 5. So the maximum value is 6, and it's basically throw off a die, right? That's what we're getting, as we would expect. Now we stop printing because that's going to just unnecessarily create lots of mess, and we start doing the experiments. Okay, let's look at the result of the experiment. Here you can see the range is wrong. So the binning has to be increased. Let's increase the number of bins to about 16. Double that, and range has to be 0. Here now I'm going to make the range 0.5 to 1.5. Sorry, 8.5. Why should it be 8? It should be 6.5. Okay, so that's just to kind of change the bins. And in that range, we want the number of bins to be not 16. Really, we have 6. So about 12 bins should be enough. So that they don't get mixed up together. All right, so let's now run that again. And these are individual numbers, 4, 5, 5. Then you got this, and then sometimes you got 6, sometimes you got 1. And here are the tosses, and you could see that 5 appeared more times than the rest of them. So the probability distribution is that it's not uniform. You expect it to be uniform for a die through, right? So let's see if it goes to being a more uniform as we increase the number of experiments. Okay, it's getting there, right? Still not exactly the same, but it's getting to be about the same, smaller variations. So those variations should decrease as we increase the number of tries. So now with 1,000, sample size of 1,000, you can see again, slight variations are still there, but they're all approaching to the value that we would need them to be. And because it's density, the actual value is less. It's not the same. Okay, so the difference now is getting smaller with 10,000, with 100,000 counts. Let's see if it's approaching certain limit. Yes, it is. It's getting even, much closer. Let's do 1,000,000 experiments. And it takes time. You can see every time I increase that. Now it's more or less uniform. So it's now a fair die. That means the random numbers generated by the program are also fair. They are they generate essentially a uniform distribution. And you can of course do lots of other cool things with it. You can change the distribution, like the Gaussian distribution for the velocities that we found. You can create random numbers following a certain distribution as well. We will take a look at that in the next class. So that's the this is something you can do with computers that you cannot do in real life experiments, right? If somebody asks you to sit down and do 1,000,000 die throw experiments to see if the die is fair, that's not practical, right? But the nice thing about computer is you can do that and you can quickly check that it works, right? So the statistical definition of probability works is what we illustrated here with the help of these two examples. And I will upload the codes, share those with you a little later today so that you can play with them as well. Okay, so let me
I
stop
have a
sharing.
question for you.
Yeah,
Can you
go ahead.
Can you share the screen again?
Sure.
Very nice.
So let's share the screen here. Okay.
Okay. Go to the arrow, please. Okay. After the plot histogram, you
Mhm.
just suddenly
Right. Yeah.
this tool came. I don't know from where, because
Yeah. So
in the
this,
above line you write, but suddenly these two lines
yes,
came and you make
for
some
these two
changes.
lines, what I did was I played with the arguments so that I cannot get a nice looking graph. And so what this does is density is true or false. It's just going to tell you it scales the changes. So let's make density equal to false and let's see what happens, right? So if I make density equal to false, what it does, it gives you exact counts. So how many number ones you got out of the 1,000,000 tries, right? So let's also make that number to be smaller. Let's make it maybe 100. Okay, and let's run this. So I made density equal to false. Okay, it tells me out of 100, I got maybe 22 of ones, 22 of twos, and maybe 16 of threes, and so on. So it gives actual count versus a scaled number. And if I increase now this to, let's say, 10,000, the scale will change. Okay, so that's what that parameter is. It just tells you now out of 10,000, 1,600s are one, right? So it's kind of natural. And if you don't want to play with that scale, you can just make density equal to true, and then it will instead give you the density as opposed to. Now the density of definition is little weird. It depends on the number of bins. It actually takes the counts, divides it by the number of bins, and then gives you that. And you can see there are bins that are empty here. So I think the closest thing that you would do is probably 6 bins, and then the things would be counted, and the density would be then appropriate to what we expect. So the largest value would be 1/6. What is 1/6? 1/6 is 0.17, right? 0.16. And you can see now the top value here for the density would be 1/6. It will actually give you the probability that you're looking for. And you can see small variations here. All the bins are now mixed up together. They're joined together because they're connected. There is no gap between them. But if we increase the result number of times, it should go to 0.167. So larger, okay, 0.167 is what the probability we expect. And you can see it's a more or less uniform graph, right? Now you don't quite get everything from there. That's why we made the bins to be a little larger. Let's make it 12. So every other bin is empty always. And when we do that, the density will go down actually. You can see now the density become larger, right? Because there are some bins that are empty. So this density is a little weird quantity. It doesn't quite give you the value of the probability. We will do some experiments later on. So these arguments, those lines came because I just had worked on it quite a bit to make sure they work properly, and to make sure I don't forget all the possibilities. I just got those arguments there. And then this part here, plot histogram, is a standard function. It accepts lots of arguments. First one, of course, is the data that you want to plot, and the bins. So the computer internally takes the number from the array and puts it into the right kind of bins. It does the bucketing for you. You don't have to do that, right? If you had to do that on a piece of paper, if you were to do this experiment by hand, what you would write down is you would write 1, 2, 3, 4, 5, 6. Every time you get a 6 in the die, let's say, you would put a bar, right? So you would do this counting notation, and that way you can keep on counting. And after you have done the experiment, you will have completed the counting, and then you will be able to plot the histogram. Does that make sense? So that was the idea. So plot hist is the function, n is the first thing. And even if you remove all of the other stuff, it will automatically correct this. So let's do a little trick here. I'm going to remove all of these things that I had, and I'm going to make it a simple x, comma bins. And I don't even need to do that really. What we need to do is plot dot hist of n with bins equal to 16. So that's the simplest function, no complicated arguments. Let's see what it gives us. Okay, so it does that for you, and it just gives you the counts. So these rest of the arguments allow you to manipulate. You can see the color also changed. So that's what I did here. When I said blue, I changed the color. So I will leave it at that. So you can use those arguments if you want, but it kind of does that. Okay, let's run that. And again, you get this. I think somehow the binning is not uniform. So there is a gap here with 12. Okay, but that kind of gives you an idea. You can play with this. I will share the code with you. And so let's stop sharing and let's